Okay?
Yeah.
Yep. All right. Let's talk about two things being, let's say y is directly proportional to x, means this, where k is some constant. And it also means that if x goes up, y is going to go up. If x goes down, y is going to go down. The inverse relationship is the opposite. In other words, if x goes down, y goes up, but if x goes up, y goes down. So that's kind of the way I remember them. Direct, I equate to both of them moving in the same direction. Inverse, opposite directions. Now, if you're going to memorize anything, memorize only these two. But realize that we can make algebraic manipulations of each of these. In other words, a direct relationship would mean that k is equal to y over x, and an inverse relationship would mean that k would be equal to y times x. So be careful about what you memorize. It can cause you to be confused as to which is which. This is true and this is true, but save those to calculate algebraically. So do you have some problems?
I actually don't. It was just kind of, we've been going over it in class, so.
Okay, I can make a few up. The typical problem would be y is directly proportional to x, and when x is equal to 2, y is equal to 6. So what would y be equal to when x is equal to 12? Y would be equal to what?
Okay, and this is direct.
Uh-huh. So there's a certain pattern you want to use every time to solve these kind of problems. First thing you want to do is solve for k, because what we have here is the general equation for this relationship. We want to find out the specific equation, because not all relationships that are direct are going to have the same k. Most of them have their own k's. So what would k be for this, based on this information here?
Um, 12?
Well, if I solve for k, k is equal to y over x. Substitute y, 6, x, 2, k equals 3. So the specific equation for this particular model is this. Once you have the specific equation, then you can figure out a y for any x. If x is 12, what's y going to be? Plug it into this right here.
4.
If x is 12, plug it in. 3 times 12 is what?
Oh, okay. 36.
Do they let you, what kind of calculator, do you have the Inspire?
Oh, yeah, I just did it. I just wrote that one down and did it.
No, I know. I'm just, do you have the Inspire CX?
Yeah.
Okay, I just got that recently myself. That is one nifty calculator. And it can do about anything you want it to do. Do they let you use that on all your tests in class, or are there things you have to do where they won't allow you to use that?
No, they let us use it.
Okay, and you can also use that on all the tests coming up, the ACT and the SAT.
I can?
I believe so. At least that's what the commercials on it. Before I got mine, I went online and I did look for some reviews of it, and their own commercial says that you can use it on all of those tests, which amazes me because it'll do an unbelievable lot of things.
Yeah.
Probably will even give you direct and indirect, or direct and inverse relationships. But that's the pattern we do. So we start out with the general equation. They give us an x and a y, so we are able to solve for k. That gives us a specific equation, and then from the specific equation we can come up with any y that you want if you give me an x.
Okay.
So let's do another one. Let's say that y is inversely related to x, and when x is 15, y is 2. So what is y going to be when x is 100? First of all, what's the general equation?
Y equals k over x.
It's the next step.
Plug in y and x.
Okay.
Or no, flip it and
Yeah, you can do it that way. You don't have to multiply it yet. In other words, I could plug in 2 for y, 15 for x. Now solve for k. It's almost easier this way.
yeah, it'd be k equals y x.
Which is what here? What number is k equal to?
30.
So what's the specific equation for this model now?
K equals 30.
Y equals what?
Y equals 30k.
30 over x.
Okay.
In other words, we only solve for k. The y and the x stay the same all the time. The k is the variable that changes from problem to problem. So k is what you use the initial information to solve for k. Then you go back and the only thing you plug in is the k. So this is the specific equation. And now if I say, what is y if x is 100? What is y when x is 100?
Um. 3.3.
Yeah. Well, actually 0.3. In other words, if I plug in 100 here for x, then y is 3/10.
Okay.
That's all you do. Let's go over a principle here. That bothers me a little bit. So let's do something here. If I say the following, you're familiar with the expression f of x. Means the same thing as y. Only it's a little handier because if we express a function as f of x, now I can say, well, what is f of 1 equal to?
1.
What is f of 3 equal to?
3.
No. I'm going to take whatever's in the parentheses and I'm going to plug it in for my x on the function. So f of 3 is 9.
Oh, okay.
What is f of 5?
25.
Okay. So, did I erase it? I must have erased it. Yeah. Back in that other problem, when we had the specific equation, which was y equals x, 100 over, what was the specific equation? What did our k come out to be? 30.
30 over 100.
30 over x. There's the specific equation. And I said, what would y be when x is 100? Well, that's the same as saying, what is y of 100? Only we don't usually use the terminology for y, so it's the reason f of x works a little bit better to talk about functions is you could say, well, what is f of 100? And what you do is you plug in 100 for x, so it would be 30 over 100. So this terminology is pretty important to learn, where when you put something in the parentheses of a function, you are to evaluate that function using this for your independent variable. X is the independent variable here. In other words, it's what might change. The y is going to change depending on what the x does. But notice in this last example, as x went up, y went down. Remember when x was, well, I forget the specifics of it. But because it was an inverse relationship, they move in opposite directions. An example of a direct relationship would probably be people's height and people's weight. In other words, if you were to go out in the general population and measure everybody's, either one, height, let's say, let's make height the independent variable, then you'd probably find that as height got bigger, weight got bigger, wouldn't you say? I mean, if you counted little kids and everything,
yeah,
that's a direct relationship. Okay? I don't know what the specific thing would be. You could say weight is equal to some k times height. And we'd have to look at the data to figure out what k is for that particular model. K could be, I have no idea what k might be there. But if they indeed are in a direct proportional relationship, we would be able to find out what k is if we had the data. Now, let's talk about stuff that is in an inverse relationship. And there's a third one called joint, which is a combination of things. One of the classic formulas from physics is the gravitational force between two planets is equal to some k times the mass of one planet times the mass of the second planet all over the distance between them squared. And this was discovered by Newton. And what this basically says is that the force of gravity between two planets is directly proportional to the mass of the planets multiplied together, and inversely proportional to the distance between them squared. So if I were to translate this into words, that's what I would say. I would say the force is directly proportional to the product of the masses and inversely proportional to the distance, the square of the distance between them, between the two masses. So these direct and inverse relationships can be in combination together, and they can be squared. In other words, you could say y is directly proportional to the square of x, like that. Or you could say y is inversely proportional to the square root of x. So they don't always have to be linear. It's the terminology really that determines whether it goes in the numerator or the denominator. Now, is what we've just covered right on key as to what you're covering?
Yeah, that's what we're doing in class.
Okay. You want me to get my book and find some problems?
Well, I actually had another
Okay.
thing.
You want to cover another subject? That's fine.
Here, hold on, let me look.
Okay.
Slope-intercept form.
Okay. This has to do with the graph of a linear equation. And a linear equation means straight line.
Yeah.
Okay? When we have it in this format, m is the slope of that line, and b is the y-intercept, which is to say the point that it crosses the y-axis. Let me draw one here where this is 1, this is 2, and I'll draw a line like that. Okay? So that slope looks to be about 1. If I had, this on graph paper, I could be precise, but slope is defined as what? Rise over run. So if I want the slope of this line, I take the amount that it goes up from here to here, and the amount that it goes over, and I divide the rise by the run to get the slope. So with this line that I drew, I tried to draw a slope of 1, where I would go up that amount and over that same amount.
Yeah.
Okay? So I can begin to write the equation of that line. If indeed the slope is equal to 1, what's the equation of the line? The specific. Again, this is the general equation. We need the specific equation where m would be replaced by a number and b would be replaced by a number.
It would be y equals 1x plus 2.
Only we wouldn't write the 1. We would say y equal x plus 2.
Yeah.
Okay. Let me make it a little harder here. I am going to give you 2 points and have you give me the equation that describes these 2 points. Without graphing it.
Okay.
So how can you figure, in other words, 2 points define a line. So if I give you 2 points and I say they're on a line, that tells you everything you need to know about the line. It tells you exactly where it is on the graph, but you have to do some calculation. But what's the first thing you always want to know about a line?
Wait, what?
What's the first thing you need to know about a line in order to come up with its equation?
It's slope.
Slope. Slope is very, very important. It's probably not apparent to you why, but when you get into higher mathematics, slope is all what calculus is all about. but slope is huge. So always remember the first thing you want to figure out is the slope. So for these 2 points, what is the slope equal to?
2.
It's the difference in the y coordinates. That's the rise.
Yeah.
Over the difference in the x coordinates. That's the run. And another way that it's usually written is y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. So to figure slope, plug in our points.
Okay. It'd be 5 minus 3 over 4 minus 2.
Which is equal to 2 over 2, which is equal to 1.
Okay.
So again, slope is equal to 1. So now that allows me to go back and write the equation a little bit nicer. So now I know that. I still don't know b. Okay, well, if I take one of my points, I know this point is in this equation. So if I plug in the x and the y value into this equation, I'll calculate b, and then I'll know the entire equation. So let's pick the point that's the lowest numbers, the easiest one to do the math, and plug in 3 for y and 2 for x. So it would be 3 equals 2 plus b. That tells us b equals 1. Now we can go back and we can write the specific equation for this line, y equal x plus 1. So that's the process for coming up with the equation when they give you 2 points. Okay? They're always going to give you either 2 points and let you come up with the equation, or they'll give you 1 point and slope. So let me give you another problem, where I will give you slope and 1 point and you come up with the equation. We'll give this one a slope of 2, and we'll say the point that's on there is 3, 5. So again, notice that if you know the slope and you know 1 point, in other words, if that point's on there and that slope is 2, that has to be the line. So all you need is 1 point and slope to define a line also. So let's start with the general equation. Y equal mx plus b. We know m. So y equal 2x plus b. How do we solve for b?
Just solve that equation.
How do you solve for b? Starting with that and this point.
Actually, I don't know.
You plug in the x value and the y value into this equation.
Oh, okay, yeah.
And then that lets you solve for b, because then that will be the only unknown variable. So I plug in 5 for y, 3 for x. Turns out that b equals minus 1. So now I can write my specific equation, which is to go back up to this equation here and put in a b of minus 1. There is my equation of that line. In other words, after you're done with the equation, it should always be y equals mx plus b, where m is some number and b is some number. So that's the goal. You start out with the general and you go to the specific. It's a lot like the direct relationships and the inverse relationship.
Okay.
In that sense. Okay, let me give you another problem, which is frequently accompanying problems like this. There's the equation of a line. what's the equation of, excuse me, what is the slope of a line perpendicular to this?
Y equals negative 2x plus 3?
No, the slope would be the negative reciprocal of this number right here because it's perpendicular. So it would be negative 1/2. The reciprocal is you turn 2 over 1 into 1 over 2 and just put an opposite sign in front of it. And if you'll think about the graph, that goes through a y-intercept of 3, has a steep slope, a little steeper than a slope of 1. And notice that if I have a line perpendicular to that line, that its slope has to be opposite sign. If this slope's positive, this got to be negative. If this slope were negative, this slope would have to be positive. And it's flatter. It's not steep. It's flat. So it's got to be a number less than 1, between 0 and 1. So 1/2 makes sense for the perpendicular lines. What is the slope of a parallel line to this equation?
Y equals 2x minus
Just what's the slope of all parallel lines? There's a line that's parallel. There's a line that's parallel. There's a line that's parallel. What's the slope of all of those lines?
2?
Yep. In other words, parallel lines have the same slope. So if I said, give me the equation of a line that has the same slope as this, that is parallel to this line, but goes through a y-intercept of 5, what would it be?
Wait.
Give me the entire equation of a line that is parallel to this line, only it goes through the intercept of 5. It would be y equal 2x plus 5. In other words, m would have to be the same because it's parallel. The only thing that would be different, let me draw that line. In other words, this is the graph of this line here. Well, if it was parallel, it would be parallel and it would go through a higher y-intercept. It would go through at 5 instead of 3. So dealing with parallel is pretty easy. Dealing with perpendicular is pretty easy. And that's the stuff you're going to have to deal with y equal mx plus b. Now, have you learned the point slope method or format yet?
Kind of.
That's a different format. And it's called point slope because that's all you need is the point, one point, and a slope. Remember in our previous example when I said the slope was 2 and it went through the point 3, 5. If I would have used point slope format instead of y equal mx plus b format, actually would have been easier to solve. Notice I can fill in everything I need. Y minus this y1 value, 5, equals the slope times x minus this x1 value, 3. So there's my equation of that line instantly. No need to solve for b or anything else. Now, if I want to get this into y equal mx plus b format, I have to distribute the 2 and move the 5 over. So that would look like what? 2x minus 6, and then y would equal 2x minus 1. So we end up with the same equation of the line as the other way. It's just we actually got it a little quicker. It really kind of depends on what the problem calls for. In other words, you may get test questions that say use the point slope format to solve this and leave the final answer in point slope format. If they ask me to leave it in point slope format, then there's your answer right there. If they ask me to put it in y equal or slope intercept format, this is the answer. Same equation, just different formats.
Okay.
How about some problems from you on some of these? Out of your book or homework or what? Do you have homework that needs to be done?
No, we didn't have any yet this week.
Really? So,
Yeah.
so you don't get homework like every night, huh?
No, not. We had a quiz just the other class, and then we started a project today, so we didn't have any homework.
Okay. All right. It's kind of tough for me to bring the problems to the session, and the reason is that since I wasn't in your class, I really don't know precisely what you're covering. I mean, I know a lot about slope-intercept format and point-slope format, and I can generally talk about it. But the real key for you to succeed in this math class is for you to bring the problems to our sessions and for me to help you get to a point where you can solve those problems. That really is what's required. In other words, for me to lecture for the hour and just talking about these things isn't really the ideal way to learn this. It's for you to bring the problems and get you to solve them. So, so I don't know. What do you want to do? We can cut our session short if you want, or you can maybe look in the chapter that you're going to cover next, and we can maybe get a little head start, or
Okay,
what?
Well, like we don't have a book that we take home,
Okay.
so I don't really have any problems.
All right.
What I can do for next time is I'll make sure I get problems.
Okay.
And then
Now, maybe you could even go to your teacher and say, can I get extra problems? Because I'm working with a tutor, and that's what we do is problems. And my belief is that you're going to get better by drilling. In other words, we should have like 10 problems on direct and indirect relationships here that we could go over. Although I suspect that you understand that now, and you don't probably need drilling on that. But that's the secret to learning, is when you come across something that you don't understand, let's just go over problems, and let's keep going over problems until you can do one your own, entirely on your own. And that's the key to successful tutoring. So why don't we call this session done? And
that sounds good.
we'll. I kind of hate to do that, and I don't like. I won't do that on a regular session because, well, first of all, the students always think it's a good idea if the session is shortened. So I won't make a habit of doing this, and that's why it's real important for you to bring problems to the table.
Yeah.
Okay? So we'll go with this shortened session this week, and then next week, hopefully you'll have a bunch of problems to do.
Okay.
Okay?
Yep.
All right, Andy. I'll talk to you next week at 5 o'clock.
Sounds good. Thank
All
you.
right. Bye-bye.
Bye.